We're going to continue our work here in 5.2 on the definite integral, trying to understand this a little bit better. Let's do a practice problem that hopefully is like what you did on your homework. We're going to approximate the area under the curve y equals x squared plus 1. We can see that part of the parabola drawn here from x equals 0 to x equals 2. And we're going to use what we call a right Riemann sum. So right Riemann sum means we're going to take this interval from 0 to 2 and we're going to divide it into two rectangles, and we're going to use the right side of that rectangle to get the height. So visually we're going to get something that looks like this, and whoops, it's going to have to go all the way up here, and we're going to find the area of those two rectangles. So we are going to say that that area, get my pen back, area will be approximately, and we're going to take the first rectangle here, so its height is going to be our function evaluated at 1 times our delta x, and then we're going to take the function evaluated at 2 times delta x. So when we plug 1 into our function, we're going to get 1 squared plus 1 is 2. Our delta x is going to be, in this case, 1. And f of 2 is going to be 2 squared plus 1. That's going to be 5. And our delta x there is 1. And so we'll get 2 plus 5 is 7. So that is our approximation to the area under the curve using our two right rectangles. Okay. So let's talk more about this idea of rectangles. So our notation for a Riemann sum is something that's going to look like a sum of f of c sub I times delta t, or it might be a delta x. I think we're going to switch. Let's maybe call that delta x in this case. So we're going to, let me bring my green pen back up. And so I'll call that a delta x. So the area under the curve, we're going to take the value of the function somewhere on that subinterval times the width of our rectangle. And so this f of c sub I times delta x represents the area of a rectangle under the curve, where the height is going to be given by, of the rectangle is going to be given by the value of the function at some point on that subinterval. It might be the left side of the rectangle, it might be the right side, it might be the midpoint, or as we'll see eventually, it could be just a random point in there. And then times delta x, the width of the rectangle. When you add all of those up, that becomes a Riemann sum, and that becomes an approximation to the area under the curve. It's an approximation as long as that value of n is finite. If we take the limit as n goes to infinity, then our delta x's, which remember are given by b minus a over n, as n goes to infinity, this b minus a over n goes to 0, and as we saw earlier, our error is going to be the value of the function at the end minus the value of the function in the beginning times the delta x. So if that delta x is going to 0 because we're taking an infinite number of rectangles, then our error in computing that area between the curve and the x-axis goes to 0. It becomes exact. It's no longer an approximation, but it becomes that exact value. And so we say area in quotes because, remember, this is, an area is always positive, and our function may be above or below the x-axis, and so it's, in a sense, kind of a signed area or a net area between the curve and the x-axis is what our summation is going to give us there at infinite sum. And so we call this the definite integral. And so we introduce now some new notation and some new vocabulary. So this symbol here, that kind of, it's supposed to look like a stretched out S to represent kind of a sum. That's an integral sign. So we will call that the integral sign. This a is the lower limit of integration, and this b is our upper limit of integration. Whatever we have here, our function, is called the integrand. And this dx, which we've seen before sort of, this is going to be, we'll call it our variable of integration. So it's communicating to us, are we integrating with respect to x, with respect to y, with respect to t? What is that? It is symbolic in that it's kind of the residual of what's happening to this delta x as n goes to infinity and the delta x goes to 0. But it's more just symbolic. And remember, this is coming from our limit. It's always this limit of this infinite Riemann sum is what this definite integral is representing. Okay. So we are going to eventually learn 4 different ways for evaluating these definite integrals. Today we're going to start with 2 of them. So one is to use the idea of area, or this idea of a signed area. So with this, when we have our function f of x is given by these straight line segments, then our integral from 0 to 4 of f of x is this signed area between the curve and the x-axis. So we can see that this triangle above the x-axis will count as a positive because, again, we're taking the f of x times delta x, and our f of x is going to be positive. So this area here is going to be 1/2 base times height, which is going to be 1/2, and it looks like the base is 2 and the height is 2, so that much is going to be 2. We'll think of that as being positive because it's above the x-axis. This part in here, because it's below the x-axis, we're going to think of as being negative. So it's going to be 1/2 base times height as well, using an area argument here. Our base is 2 and our height is 1, so we're going to think of that as having an area of 1, and because it's below the x-axis, we'll think of it as being a negative 1. Our integral then is going to be that kind of net area, if you will. It's going to be the 2 plus the negative 1. It will be 1. And so we can use an area argument to evaluate this definite integral. Now, the second one we're looking at is, here is our curve, y equals the square root of 1 minus x squared. You may recognize that as a semicircle. So you may not. If you square this out, so if we square both sides, this becomes y squared is equal to 1 minus x squared. And if we add that to that minus, add an x squared to both sides, you may better recognize this as being a circle centered at the origin with radius 1. When we have y equals the square root of that, we get the top half of that full circle. So we're not including the part below there. That's not a function. So we are talking now about what is this area between the curve and the x-axis. So using our area argument, we know that this is going to be 1/2 because it's a semicircle, and then pi r squared is the area of a circle. This circle has a radius of 1, so that's going to be 1/2 pi times 1 squared, which is going to be pi over 2. So this is all above the x-axis. So using our area argument, we're going to say that this integral from negative 1 to 1 of the square root of 1 minus x squared is equal to pi over 2. Now, the next way that we're going to learn today is to use our calculator to compute this area under the curve. So this you're gonna like, I think. And so there are 2 ways we can do this off of our calculator. So the first one is using what we'll call FN integrate. And so we're going to go to your calculator, and if you go hit the math button, so first hit the math button, and then if you arrow down to option number 9, So option number 9 is FN integrate. When you hit enter, it depends on how new your calculator is. If you have a newer model, it's going to look like very suggestive of what we have just said we get here. You're going to get something that looks like this. So what you will do here is that should be where your cursor is. We're going to put in our lower limit, so you'll hit -1. Then if you go up arrow, that will put you into this spot here, and you can just hit 1 there. Then you can get right arrow, and that's going to put you right here. Now, sometimes you can just enter that, so we can just hit x squared and then -1. You can also, if you have already entered this function into your graphing menu, you could just put y1, that is variables, right arrow, enter, enter, and then the next thing we're going to do is we'll go to this place, so go right arrow, and then we'll always integrate with respect to x. So you can just hit the x comma t comma theta button, and then when you hit enter, you should get then a -1 point, and it's going to be 3 repeating. We'll round it to 3 decimal places. And we're getting a negative because, as you can see from the picture, the curve is below the x-axis from -1 to 1. So you can see that an integral can be a positive number, a negative number, or even 0, because it's giving us that kind of net area between the curve and the x-axis. Now, the second way we can do this is to go to y equals, and let's plug in our function there. So you can put in our x squared -1 into that y1, and then if you let's just, to make it look the same, go zoom 6, so you have a standard 10 by 10 window, and you should see the graph of our parabola, something like that. Now, from the graphing screen, if you go second and then to the trace button, so that we can get to the calculate menu there. So second, trace, and then if you arrow down to option number 7, it looks like an integral of f of x, hit enter, and it will give you a prompt that says lower limit question mark. And what we want to do then is just type in -1. So you're going to go -1 and then just hit enter, and it will fill that in as your lower limit, and then it's going to ask you the question upper limit, and we'll just type in the number 1 in our case and then hit enter. And it's kind of cool because you'll see it shaded much like what we see here, and then it will give us our answer on your screen that's going to say the integral of f of x dx is equal to, and it's a -1.33, and it repeats again, but we'll just round it to 3 decimal places. Now, it's really cool, and it's a nice visual to see what's going on the graphing menu, but anything that you ever do on, say, an AP exam question or my test, you want to use the FN integrate, because whatever the algorithm is that this uses, sometimes the graphing one will not give you accurate answers to 3 decimal places, but the FN integrate will. So it's nice to see, but we want to use the other one when we're actually computing something that we need an accurate answer for. And just to emphasize, this is the value of the integral. It is not the area between f and the x-axis. And so you will have to be careful what the question is asking, how you will answer it. So, for example, on the next one, we're going to look at the integral from 0 to the square root of 2 pi of the sine of x squared. So let's go to our graphing menu. We'll clear off that x squared minus 1 that we just put in there, and let's put sine of x squared. Now check your mode, make sure you are in radian mode, because we will always be in radians. Let's do, for a window, let's choose our x min to be 0 and our x max to be the square root of 2 pi. So we can go second x squared 2, and then second that little caret symbol there, and we'll go to the square root of 2 pi. Let's choose for our y min -1 and our y max a +1, and because that's all we need to know. Our sine values aren't going to be any bigger or smaller than that. When you graph it, then you're going to see something. I'll try to put it on here for you just to make sure we're looking at the same thing. We're just going to be seeing something that does something like that. Now, if our question is the first one here, what is the integral from 0 to the square root of 2 pi of the sine of x squared dx, then we will just go to math, option number 9, and we'll put in for that lower limit 0. For the upper limit, we'll go second square root of 2 pi. And you can right arrow, and for our function, you can just go variables, right arrow, enter, enter. That'll put in y1, and you can go dx, and when you hit enter there, you should get to 3 decimal places, 0.430. Now, remember what this is giving us is a kind of a net area. It's taking this, which it will consider positive because we're taking these positive function values times the delta x's, but then it's going to count this as a negative. And so what we're seeing from the 0.430 is going to be that net area, that the stuff that's above the x-axis minus the stuff that's below the x-axis. Now, if we want the true area between the curve and the x-axis, we can do one of two things. We could say the integral from 0 to the square root of 2 pi of the absolute value of sine of x squared, and then we would put the dx in there. So we could take our function and put it in the absolute value. Then it's going to count this stuff that's below the x-axis and turn that into a positive. The second way we could do is to try to find out where that is going to be 0, and I think we can figure that out because we know that the sine curve, our normal sine curve, looks something like this. So it's going to equal 0 when that is pi, and so that is when our square root of 2 pi is going to be pi. And so I think what we're going to get there is going to be, let's see, what would that be when 2 pi is going to be pi squared? So that's, let's see, when we want the, I'm sorry, we want the x, hold on there, let me back up. So that's when our x squared, because that's what's in our function here, is our x squared is equal to pi. So that's going to be when we have a square root of pi. So the second way we could do this is we could say, let's take the integral from 0 to the square root of pi of sine of x squared. And that's going to count all of this stuff right here. And then we can go minus the integral from the square root of pi to the square root of 2 pi of sine of x squared, because this minus will the integral would give us this negative value, but our minus sign will turn that around and add it to it. So if we're going to use our calculator, this method is going to be the easiest. But if you're not able to use your calculator and you're going to have one that you have to do by hand, then we'll need to use this one. Let's go ahead and do it this way. I think that's going to be the easier. So we can go math 9 again. So math 9, we'll go from 0 to, and again, we'll go second square root of 2 pi. Oops, I did that wrong. Let me try that again. We want to go to the square root of 2 pi, and then I'm going to drop down And once I'm in the parentheses, I'm going to go math, right arrow, and then you'll see absolute value is the first one. So if you hit enter and then hit variables, right arrow, enter, enter, it'll put that y sub 1 in absolute values. Then right arrow till you're in the dx box and hit your x. And then if you hit enter, it's doing some work there on mine, I'm going to get 1.359 is going to be that area between our curve and the x-axis between 0 and square root of 2 pi. Okay, let's talk a moment about more generalized Riemann sums. So we have been talking about so far uniform width Riemann sums. We have been choosing those delta x's to be b minus a over n. Those are all the same, which we will call uniform width. Now, in a more general case, our Riemann sums do not have to be uniform width. So we can, for example, imagine that we're going to divide this up into n subintervals, but maybe we're going to choose our x sub 1 to be here, and then maybe we're going to make our x sub 2 here. So I'm trying to make these very clearly different widths. And then maybe we're going to pick our x sub 3 over here. And so on. We continue this where we're making all of these delta x's different widths. Now, we can say then that our Riemann sum is going to be f of, and we can take whatever value of x on this first subinterval. It could be the left side, it might be the right side, it might be the midpoint, it could be any other point. And then we're going to multiply that by that first delta x. And then we can take the value, the height to be the value of that function on that second subinterval, wherever we like, times its delta x, and then so on. And so what you're going to see then as we get out there is that our Riemann sum will look slightly different. Our summation is going to go from I equals 1 to n. We'll have f of c sub I, but instead of just calling this delta x, we're going to call it delta x sub I. So this is a more generalized Riemann sum. And now what we want to do is we're going to introduce this new notation and new vocabulary and symbolism. We're going to call a double bar delta symbol here. That's what we're going to call the norm. And the norm is equal to the largest of all of the delta x sub i's. So it's the largest delta x that appears out of all of our choices. So if we now then, in our more generalized case, we're going to say the limit as the norm goes to 0, that is, as our largest delta x goes to 0, of our sum I going from 1 to n of f of c sub I delta x sub I, that is going to be, in general, our integral from a to b of f of x dx. So that's the most generalized definition of our definite integral. Okay, very good.